I will mostly focus on the gamma rays, and the gamma rays are the things that are highlighted here in green on this beautiful collage of things that were put together for KIPAC at 10. Okay, I think I don't need to give you a motivation for dark matter in the universe. I just briefly mention something that I found quite interesting in Jonathan Feng's SNOMAS summary. Dark matter is really not only about galaxy rotation curves. We know that dark matter exists for many, many other reasons, and these are listed here. And according to Jonathan, we are now entering the age of dark matter identification, and I very much hope that this is true. This is the other slide I loved at the SNOMAS meeting. This is a slide from Tim Tate, and it's his depiction of the various theories of dark matter. And I think it echoes Bert's point in saying that we really don't know much about it. But of course, we're trying to look for it. And this is the third thing that I want to briefly mention with regards to SNOMAS. It became really apparent there that there's an interplay of different detection capabilities that the colliders, the direct detection experiments, and the indirect detection experiments have. And in conjunction with simulations and astrophysical observations, we really need all of them to try to address the dark matter problem, because we don't know which of these will first see dark matter. Okay, so I talk about the indirect detection of dark matter. So the idea is rather straightforward. Supersymmetric neutralinos in this case, annihilate, produce all kinds of standard model particles, and then eventually what comes out are either cosmic rays, so positrons, electrons, protons, etc., or gamma rays. And as I go along, I will focus on the gamma rays. I think I don't need to say much about this, only that, again, there's a huge range of predictions for the mass and the annihilation cross-section. So here is a plot that shows various models in the mass versus interaction cross-section space. And for those of you that sit up close, you realize that there are about 51 orders of magnitude here, and there are about, let's see, 63 orders of magnitude here. So we really don't know very much about where exactly to look, which is a problem for the experimentalists. And in the following, I will follow Michael's advice and focus on the WIMPS. And the point to make here is that it predicts a mass of the dark matter particle of around 100 GeV, and it predicts annihilation cross-sections of the order of this thermal rally cross-section, which is 3 times 10 to the minus 26, and this will become important later. Okay, I said that. So the problem is, of course, that the gamma rays from dark matter annihilation have 2 components. So if you want to predict the number of gamma rays per energy bin that you get out, you have 2 factors. There's a particle physics factor that has all the cross-sections and the branching ratios, etc. in it. And then there is the astrophysical factor that is basically given by the squared density of dark matter in the universe. Of course, if we ever detect them, we could start to measure these things. But given that we haven't detected anything, we can make assumptions about this part and constrain this part. And this is what generally is done. Okay, so now going to gamma rays. So if you say you want to detect gamma rays, then you basically have 2 options. You can either put your instrument outside of the atmosphere, which is what we have done with the Fermi-LAT, and that is ideal for lower energy gamma rays, because gamma rays typically come with an energy spectrum that falls exponentially with energy. So this exponent here typically is a large number, larger than 1 certainly. And then the second way how you can detect gamma rays is you can use the atmosphere as part of your detector. And the idea here is that the gamma ray comes in, enters the atmosphere, pair produces in the atmosphere, interacts with the atmosphere to produce a particle shower, just like in your particle detector, and the particles in this shower, the charged particles in this shower, move faster than the speed of light, and thereby emit Cherenkov light, which is optical light, that you can then see on the ground if you have telescopes with big mirrors, and you have cameras that can basically see this light and can can give you an idea about the light distribution of the air shower, and therefore the particle distribution of the air shower, and therefore the properties of the primary particle. And these ground-based detectors, as I will show later, are ideal for high-energy gamma rays because you can basically spread them over large areas and therefore have a very large sensitive detection area. Okay, this is the most recent gamma ray sky above 1 GeV taken with the Fermi-LAT, 5 years of data. We recently celebrated our 5th anniversary in space, very happily. And the nice thing about this is, I don't want to go into the details of this map, but of course, as was alluded to earlier by Neil, the nice thing about the Fermi Gamma Ray Space Telescope, and in particular the LAT, is that it sees the whole sky all the time, and therefore we can look for dark matter in very many places. We can look for it in the center of our galaxy, we can look for it in the halo around the center of our galaxy, if this place is too bright in astrophysical foregrounds. We can look for it in galaxy clusters, in dwarf satellites, etc., etc. We can look for spectral lines. We can even look for other particles, not only gamma rays. We can look for electrons, for positrons, and so on and so forth. And we did all of that. And as I will show you in the following, unfortunately, we haven't detected dark matter yet. Okay. Nevertheless, there are about, when I last looked, there are about 370 dark matter-related publications that are that have some connection, either analyze Fermi-LAT data or make predictions for Fermi-LAT in the future, or address theoretical questions with these data. And I will highlight a few of them. By far the highest cited Fermi science paper is a paper about a measurement of the electrons, not the gamma rays, which is somewhat ironic because, of course, we are a gamma ray detector, but nevertheless, this received a lot of attention, the measurement of the electrons. You can see it here compared to previous measurements, and you can see that our error bars are really tiny because they're very, very hard to see, even though we included systematic errors. And then the other thing that you can see is that there is a slight overshoot compared to a standard, well, somewhat traditional model that was that people came up with pre-Fermi-LAT launch for how electrons and positrons can be generated by the interaction of cosmic rays in interstellar material. And this tiny little bump over this blue line gets some people very excited because you can possibly detect dark matter signatures not only in gamma rays but also in charged particles. Even more exciting is this graph where you can see the positron fraction, that is the ratio of positron flux to the sum of electrons and positrons, and you see that it has a rather sharp rise, which is by now firmly established, and Fermi did one measurement that established this, followed up by a measurement by AMS, which did this actually with exquisite precision. And if I were to plot the model for the secondaries again on this graph, it would drop something like this. So there's a huge discrepancy between what we expect just simply from the interaction of cosmic rays and what we measure. And this could be a sign that what we are seeing is a sign of the annihilation of dark matter. Unfortunately, by now, this is mostly ruled out by other measurements. So I think it's fair to say that most people by now believe that this positron fraction probably has an astrophysical origin because there are lots of astrophysical sources around us, and we know they generate electrons, and we know they generate positrons. For example, pulsars, but also others. And in particular, if you look at the gamma rays, you can actually constrain a a lot of the models that were invoked to explain this Pamela excess with dark matter. So here are some of the early areas in dark matter versus annihilation cross-section phase space, where this was somehow the sweet spot of the models. And as you can see, some of these models are already ruled out. And I think by now, with more updates to the data, I think most of these models are ruled out. Okay, so moving along with other targets where we looked for dark matter, the most promising target is to look for dark matter in dwarf spheroidals, because they are largely free from astrophysical sources that can produce gamma rays, and they are also very much dark matter dominated. We have actually done a stacking analysis, and this was very much done here at SLAC, of about 25 objects, and we found no signal. And we were able to put limits, and actually for the first time, we were able, with these limits, to move below the thermal Rayleigh cross-section of 3 times 10 to the minus 26 that I mentioned before for some small range of the mass parameter space. In the future, we expect to improve that. So this is where we expect the limits to be with 10 years of Fermi operation and 10 more dwarfs, because we expect to find more dwarfs with instruments like DES and LSST. Okay. We've also looked in clusters of galaxies. The problem there is that the exact amount of substructure is not very well known in the dark matter density distribution. And this is very important, of course, because the density enters quadratically. If you make rather a conservative assumption about the density distribution, you get limits that are in the range of 10 to the minus 24, so not very competitive with the dwarf limits. But of course, you could be lucky, and if there's significant substructure, maybe in the future you could see a signal there. Also, we looked in the halo of the galactic center. So we used a surge region above and below the galactic plane to stay away from astrophysical gamma rays a little bit. If you make the most conservative assumption in saying that you don't know anything about the sky, the gamma ray sky, and just put limits on dark matter, you come up with a line that looks like that. Somewhat more realistically is that you take into account what you know about the dark matter sky, what you know about the diffuse emission and the sources, and you get limits that are somewhat compatible or comparable to the limits that we see in dwarf spheroidal galaxies. Okay. So if you want to put all of this together, I've made this plot that shows all the limits on one plot. So the galaxy clusters I mentioned are not as stringent as the other ones, but then the dwarf spheroidals, the galactic center halo, and the isotropic diffuse that I didn't have time to talk about, they are basically all more or less in the same ballpark, and they are all starting to eat in this thermal relic cross-section, which is, of course, very interesting in terms of WIMP parameter space. Okay. Now, I want to make a slight excursion and talk about lines. Probably most of you know that in early 2012, there was a claim from Christoph Weniger, who's actually not a member of the LAT team, that he found a line in the direction of the galactic center at 130 GeV. The significance, after taking trials into account, was 3.3 sigma. This signal was actually slightly offset from the galactic center, but there were theorists that came up with a way of describing how that can happen. This received, again, a lot of attention so basically within a year, it reached about 180 citations by now. Unfortunately, follow-up studies, and again, very much done here at SLAC, showed that there are problems with this signal, and that this signal is probably an instrumental effect. So the first problem that was obvious quite soon after the discovery was that if you look into the gamma rays from the limb of the Earth, the limb is a very bright gamma ray source because of interaction of cosmic rays with the atmosphere, producing gamma rays. You actually tend to see a hint of a line at 130 GeV as well. And of course, you don't expect a line from the Earth limb because that's simply interaction of cosmic rays with the atmosphere. So that points to an instrumental effect. In addition, if you plot the time evolution of the signal, so this is the accumulated significance as a function of time. This is the point where the data set at which the claim was made, and this here shows the time evolution of the signal. Actually, the signal seems to be going down as we take more and more data into account. And this is clearly not what you would expect the signal to be, which are these green lines, and is more in line what you would expect the signal to do if it was a statistical fluke. In addition, if you take into account the energy resolution of the Fermi-LAT in the fitting, you actually realize that the signal is way too narrow given the energy resolution of the signal. So if you take the energy resolution in this maximum likelihood fit into account, the significance of the signal actually drops to something like 2 sigma. And also, I mean, the time evolution also doesn't show you anything going up. So I think by now, probably most people are convinced that this signal is not a true signal and probably was an instrumental effect. What exactly it was, we don't quite know, but that's the current status of things. And therefore, we can put upper limits on annihilation into photon lines, and they look something like this, depending on your dark matter profile, etc. Okay. So I briefly want to talk about what's next. So the Fermi-LAT is basically the largest thing you can lift into space on a delta rocket. We had to use a delta heavy configuration. So what can you do? Well, one thing you can obviously do is assemble a super-LAT in space, but that's going to be very expensive. You can also put several Fermis on the moon, and there was talk about this for a while, but now the race to the moon seems to have gone away, and I think this is no more in the cards, really. So the most obvious thing to do is go to the ground and improve the instruments on the ground. And there's actually a plan in the works to do that, the Cherenkov telescope array, which would follow up on the existing arrays. The existing arrays have of the order of 4 or 5 telescopes. And the plan for the Cherenkov telescope array, CTA, would be to have of the order of 100 telescopes to enhance the sensitivity by about an order of magnitude. It has a very aggressive construction plan. The first science, we hope to put the first telescopes on the ground in 2016 and complete the array by 2019, depending on funding, of course. The collaboration is very large. We have about 1,000 people in 27 countries, and these countries are listed here. Here you see them on a map. So if your country is not in CTA, then you should think about joining. One thing that people always ask me when I talk about CTA is where it will be built. The plan is to have 2 sites, one in the southern hemisphere, one in the northern hemisphere. There's currently a site study going on. So there are 3 sites in the south, Namibia, Chile, and Argentina. And in the north, the proposed sites are Canary Islands, and then in Baja California, and in Arizona near Meteor Crater. And we're currently evaluating these sites and are about to decide where to put our southern array. In parallel, we are building prototypes. This is one of the prototypes, not at the final site, of course. I just put where the sun would be, in principle. This is actually in Berlin, close to Desitzheuten. This is the same site, but in sunny weather. So we have built the first prototype telescope and are about to mount a dummy camera on that. And as I said, this is going on. So why do I tell you all of this? I want to show you what the reach of CTA is for WIMP dark matter. So I showed you this plot before. CTA will address the higher energy range, and the limits that we can expect, or the sensitivity that we can expect for CTA for observations of the galactic center halo are here, shown here. So the combination of the Fermi-LAT and CTA will really be able to rule out a large part of the WIMP parameter space. Now this is for the channel of main annihilation into BB bar. You can also look at real models, like in this case PMSSM models. So this is the usual WIMP mass versus annihilation cross-section. Here is 3 times 10 to the minus 26. And these are all models that obey all current dark matter constraints. And you can see that CTA will significantly eat into this parameter space. This is my final plot that shows again the complementarity, again for these PMSSM models. Every dot, in this case, it's the mass of the neutralino versus the spin-independent scattering cross-section. And every point here is one model that obeys all current limits. And the color coding is such that the green points will be excluded by direct dark matter experiments, but not indirect. The blue points will be excluded by indirect, in this case CTA, but not direct detection. The red is where both will see these models, and then these purple ones are the ones that LHC will see. And the point that I want to make is that there truly is a complementarity between these different techniques, and depending on which model nature really realized, we can hope to see dark matter in either one or several of these techniques. Okay, so I stop here. Congratulations again, KIPAC, for 10 years of great science, and hopefully, like Michael said, when we reconvene in 10 years, we might have found something. Okay, thank you. So the question was whether there are still people who believe in MOND. Okay, so I'm probably the wrong person to answer this question, but I mean, I think there are still people who believe in MOND, yes. I think the number of people that believe in MOND shrinks, but I think there are still people who believe in it.
Do you really think it's excluded? You showed it's not a theory.
Yeah, I mean, okay, Michael, I don't know if you want to say something about this, but
I mean, it's not a theory. It's a clever way to fit. It's like Bode's law. It's
yeah.
a clever way to fit rotation curves. End of story. It
Yeah.
doesn't predict anything.
Yeah, I mean, my understanding was also that the measurement of the bullet cluster posed very serious problems for any description of that with MOND, but yeah. The reason why there is a threshold at low energies, below which you are not very sensitive, is that the smaller the energy of the gamma ray, the smaller the shower in the atmosphere, the less strength of light is produced. So, but you need enough light to trigger your detector. So you basically have two options. You can either move your array higher in the atmosphere, go to a large mountain. That has the problem of making it harder to operate. And then the other option is you can build more very large telescopes, because the larger your mirror, the more light you can collect. That is a strategy you could go. The problem is the large telescopes are way more expensive than the mid-sized ones. So there's some trade-off of where you want your best sensitivity to be given a certain amount of money. And so that's basically the trade-off. And then, of course, you have to take into account that below a certain energy, it doesn't really make much sense for CTA to go there because it's very, very hot, and Fermi is doing great work. So if you take all these things into account, I think the plan that CTA currently has, which is go to an altitude of something like 2 to 3 kilometers where you could easily operate and have 4 large-sized telescopes, presents a reasonable compromise between these things.
We've now determined omega matter, h squared, the reduced Hubble constant, and we've determined omega baryon, h squared. And they differ by 20 sigma.
Mm-hmm.
And so within the framework that we currently work, the standard cosmology and the standard model, we have a 20 sigma problem that says dark matter is not a baryon. And so I think that is something we should really pursue, because it may not be true. It may be that Mond is right or something else is right. But in order to make that happen, you have to tear apart this whole foundation of the standard model of cosmology and the standard model of particle physics. And you know, the bullet cluster, who cares about the bullet cluster? It didn't teach us anything. The real thing is that we've measured omega matter h squared with a very, very tiny error bar, 0.12 or something, and omega baryon h squared, 0.022, and they differ by 20 sigma.
Yeah.
And so that's the prize, is that we've worked ourselves into a corner where the dark matter can't be baryons. Otherwise, we have to give up either the standard model of cosmology or the standard model of particle
That's a
physics.
good point, yeah.
We have time for one last question. Not in this session, but for the 5% and thinking of the next 10 years, as you look into your Christmas ornament and think about the astrophysics that CTA will do over the next, in 10 years' time, what personally excites you the most? What do you think is going to be its biggest area of opportunity?
Okay, so I personally think that the biggest area of opportunity in terms of astrophysics is the time domain. I mean, you have, if you are able to observe a flare from a blazar or something like that, you will just be blown away by the amount of data you have. You will be able to measure flux changes on second timescales and things like that, and I think that will be very exquisite.